Hello everybody, we would like to show you a short video about the Discrete Fourier transform. So let's start with the definition. So the definition of DFT. DFT is a finite duration discrete frequency sequence which is obtained by sampling one period of Fourier transform. Sampling is done at n equality spaces points. At this formula we have xn is a discrete sequence and x key is discrete Fourier transform. So k we have from 0 to n minus 1. Since the summation is taken for n points, it's called as n-point DFT. Also, we have like IDFT, which is obvious inverse DFT, so we can like denote it by the next formula.
Previous equation we had a term e power minus g to p divided by n. Now we will denote it by wn and we'll call it a twiddle factor. Twiddle factor makes the computation of DFT a bit easy and fast. Using twiddle factor we can write equations of DFT and other IDFT as under.
The DFT maps capital N numbers, the values of time domain signal axis into a new number of values of frequency domain signal, x capitals. So we are taking n numbers, mapping into a new n numbers. So we have to represent it, we can represent it as a square matrix n multiplied by n and a vector n multiplied by 1 of signal values. So we will get frequency domain coefficient. So when we denote Wn like e power minus j to p divided by n, it is our twiddle factor. So then we can derive the previous formula as multiplication, derive the sum as the sum of multiplications, where we will have x our columns and w rows. So we will, for each k, we will rewrite it as different powers. For k equal 0, we will have x capital 0 is equal the vector WNO, 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 WNO multiplied by x0. In the same way, we can obtain the others vectors.
So from the previous example we can define the general formula for the DFT coefficients. So we denote the one column vector x that have n capital elements x0, x1 and xn minus 1, and x capital that have n capital elements x0, x1, xn. So from that we can obtain the general coefficient DFT formula that x capital is equal to matrix multiplied by x. And below we have the formula that just represent all the products of the matrix and the column vector.
So now let's talk about what the inverse DFT is. The previous equation tells us that x is equal w multiplied by x. It's the DFT, so when we rewrite it like x equal multiplied by w power minus 1 multiplied by x capital, it will be the inverse DFT. We can rewrite it as xn equal 1 divided by n, and on our sum with x capital we have to divide by n to keep our equation true. So let's rewrite it like multiplication of matrix and vector. We will have that w multiplied by w power minus 1 will give us identity matrix. So from this equation we can rewrite w minus 1 as the same matrix as w, but with negative powers. So when we have, like, for example, number 2 in power minus 1, it will be like 1 divided by 2, and when we multiply it by 2, it will give us 1. So the equal is true.
So all this leads us to the notion of the basis vector. So let us denote the WL as the L's column of matrix inverse. Then we can define the X as the products of matrix inverse and DFT coefficients. So we can span the columns of matrix inverse, and we see it in the formula on the right side. And all this leads us that W1, W2, Wn are basis vectors for representing X. So from this we see that WL in general as column vector is a complex sinusoid with frequency L to P divided by N. Thank you for your attention. We hope this video will help you to better understand discrete Fourier transform.